Every minute you spend alive, you are 1 minute closer to the extinction of everything you have ever known, everyone you have ever loved, and every trace of the civilization that raised you. And the terrifying part is not that it will happen, but that most people have absolutely no idea how many different ways it could happen, or how close some of those scenarios have already come to unfolding. This is not fear-mongering. This is the raw, unblinking reality that science, history, and mathematics present to anyone brave enough to look directly at the data. The question is not whether humanity will face existential threats. The question is which one gets us first, or whether we possess the collective wisdom, discipline, and courage to outmaneuver every single one of them forever. That is a tall order for a species that has existed for roughly 300,000 years on a planet that has been systematically exterminating its own inhabitants for 4.5 billion. So let us begin where the evidence begins, with the merciless record of mass death that Earth itself has authored. Long before a single human being drew breath, Earth's fossil record is essentially a graveyard stacked on top of a graveyard stacked on top of another graveyard. And the numbers are staggering. Over 99.9% of every species that has ever lived on this planet is already extinct. That statistic alone should be enough to shatter any illusion that humanity occupies some protected category in the biological ledger. The average lifespan of a mammalian species is roughly 1 to 10 million years, depending on which paleontological dataset you consult. And Homo sapiens has only been around for approximately 300,000 of those years. By the cold arithmetic of evolutionary history, we are not veterans, we are newcomers who have barely unpacked 5 times in Earth's deep past. The planet has experienced what scientists classify as mass extinction events. Episodes so catastrophic that they wiped out anywhere from 75 to more than 90% of all living species in geologically brief windows of time. The first of these so-called Big Five struck around 445 million years ago at the end of the Ordovician period, when glaciation and falling sea levels devastated marine life on a planet that had not yet produced a single land vertebrate. The second arrived roughly 375 million years ago during the late Devonian, when reef ecosystems collapsed and oxygen levels in the oceans plummeted over a span that may have lasted millions of years. The third, and by every measure the most terrifying, came at the end of the Permian period, approximately 252 million years ago. The Permian-Triassic extinction event, sometimes called the Great Dying, annihilated an estimated 81% of all marine species, roughly 70% of terrestrial vertebrate species, and about 57% of all biological families on the planet. Some datasets place the marine species loss as high as 96%. The trigger was not an asteroid, it was the Earth itself. Specifically a titanic episode of volcanism in what is now Siberia, known as the Siberian Traps. A flood basalt event that poured lava across an area larger than the state of Alaska and released enough carbon dioxide and sulfur gases to acidify oceans, stripped the ozone layer, and pushed global temperatures to levels that made most of the planet uninhabitable for complex life. The fourth mass extinction occurred at the end of the Triassic, around 201 million years ago, clearing ecological space for the rise of dinosaurs. And the fifth, the one everyone knows, the one that has been dramatized in 100 Hollywood films, arrived 66 million years ago at the boundary of the Cretaceous and Paleogene periods, when a 6-mile-wide asteroid slammed into what is now the Yucatan Peninsula in Mexico at roughly 45,000 miles per hour, releasing energy equivalent to billions of Hiroshima-sized nuclear weapons detonating simultaneously. The Chicxulub impactor, as it is now known, created a crater more than 110 miles in diameter, launched superheated rock vapor into the atmosphere, ignited wildfires across entire continents, triggered megatsunamis, and blanketed the planet in a cloud of dust and sulfur aerosols, so thick that sunlight was blocked for months to years. Photosynthesis collapsed, food chains disintegrated, and approximately 76% of all species on Earth, including every non-avian dinosaur, vanished forever. These are not myths. These are events documented in rock, in isotope ratios, in the sudden disappearance of fossil lineages across stratigraphic boundaries on every continent. And they carry a single, inescapable lesson: extinction is the norm, survival is the exception. And no species, no matter how dominant, no matter how intelligent, no matter how convinced of its own permanence, is exempt. The asteroid that ended the age of the dinosaurs was not a one-time cosmic accident. Our solar system is littered with rocky debris, remnants of the primordial disk that never coalesced into planets, and thousands of these objects cross or come near Earth's orbit on a regular basis. NASA's Center for Near-Earth Object Studies tracks what are formally designated as potentially hazardous objects: asteroids and comets whose orbits bring them within roughly 4.65 million miles of Earth, and whose diameters exceed about 460 feet. As of recent catalogs, more than 300 such objects have been identified, and new ones are discovered every month. The probability of a Chicxulub-class impactor, something 6 miles wide or larger, striking Earth in any given year is extraordinarily small, estimated at roughly 1 in 100 million, which translates to about a 0.00001% chance annually. On paper, that sounds like a risk you could ignore for the rest of your life and the lives of your grandchildren and their grandchildren after them. But probabilities and consequences are two different things, and when the consequence is the termination of all complex life on the planet, even a tiny probability demands serious attention. Moreover, asteroids do not need to be 6 miles wide to cause civilizational damage. A rock just 500 feet in diameter, striking a major metropolitan area, could kill millions of people outright and cause hundreds of billions of dollars in damage. A rock a mile wide could trigger a global climate disruption lasting years. And the frequency of these smaller but still devastating impacts is far higher than the extinction-class events. NASA estimates that a city-destroying asteroid impact, something on the order of the object that created Arizona's meteor crater roughly 50,000 years ago, occurs roughly once every 1,000 years on average. In 1908, a relatively small asteroid or comet fragment, estimated at only about 120 to 200 feet across, exploded in the atmosphere over the Tunguska region of Siberia with the force of roughly 5 to 15 megatons of TNT, flattening 830 square miles of forest, an area larger than the city of Houston. Had it arrived 4 hours and 52 minutes later, the Earth's rotation would have placed St. Petersburg, then a city of over 1 million people, directly beneath the blast. In February 2013, a meteor roughly 66 feet in diameter entered the atmosphere over Chelyabinsk, Russia, at approximately 40,000 miles per hour, producing an airburst equivalent to about 500 kilotons of TNT, roughly 30 times the energy of the Hiroshima bomb. The shockwave shattered windows across 6 cities, damaged over 200 buildings, and injured approximately 500 people, mostly from flying glass. The Chelyabinsk event was a reminder that cosmic impacts are not relics of deep time. They are ongoing, unpredictable, and potentially catastrophic even at modest scales. The asteroid Apophis, a 100-foot wide near-Earth object, briefly generated worldwide alarm in 2004 when initial orbital calculations gave it a 2.7% probability of striking Earth in 2029, a probability later revised downward to effectively 0 after additional observations refined its trajectory. Apophis will pass within roughly 19,000 miles of Earth's surface on April 13, 2029, closer than the geostationary satellites that carry our television signals, but it will not hit us this time. The critical point is that while humanity now possesses the telescopic infrastructure to detect most large asteroids years or decades before a potential collision, detection alone does not guarantee survival. Deflection is required, and for the first time in human history, we have at least a proof of concept. On September 26, 2022, NASA's Double Asteroid Redirection Test, the DART mission, deliberately crashed a 260-pound spacecraft into Dimorphos, a small moonlet orbiting the asteroid Didymos, at approximately 14,000 miles per hour. The impact successfully altered Dimorphos's orbital period by roughly 33 minutes, far exceeding the minimum benchmark of 73 seconds that mission planners had set as the threshold of success. DART proved that kinetic impactor technology works. If you hit an asteroid hard enough, early enough, you can nudge it onto a trajectory that misses Earth entirely. But DART was a test against a small, non-threatening target under controlled conditions. Deflecting a true extinction-class asteroid hurtling toward Earth on short notice would be an engineering challenge of an entirely different magnitude, and it is not at all clear that current technology could accomplish it. The sky is not safe. It has never been safe. We have simply been lucky, and luck, as every gambler knows, does not last forever. Beneath our feet lies a threat that many geologists consider statistically more dangerous than an asteroid impact. Supervolcanism. A supervolcano is defined by its capacity to produce an eruption measuring 8 on the volcanic explosivity index, meaning it ejects more than 240 cubic miles of material in a single event. For comparison, the 1980 eruption of Mount St. Helens in Washington state, which killed 57 people and caused over $1 billion in damage, expelled roughly 0.07 cubic miles of material. A full-scale supervolcanic eruption would be thousands of times larger. Earth has experienced these cataclysms repeatedly throughout its history, and the geological evidence suggests they occur roughly once every 100,000 to 700,000 years, making them far more frequent than extinction-class asteroid impacts. The most famous recent example, recent in geological terms, is the eruption of the Toba supervolcano on the island of Sumatra approximately 74,000 years ago. The Toba eruption was one of the largest volcanic events of the past 2 million years, ejecting an estimated 670 cubic miles of rock and ash, and creating a caldera roughly 60 miles long and 18 miles wide. The eruption injected colossal quantities of sulfur dioxide into the stratosphere, where it formed aerosol particles that reflected incoming sunlight and triggered what is known as a volcanic winter, a period of dramatic global cooling that may have lasted 6 to 10 years. Some researchers have hypothesized that the Toba eruption reduced the global human population to as few as 3,000 to 10,000 breeding individuals, creating a severe genetic bottleneck that nearly drove Homo sapiens to extinction. This hypothesis remains hotly debated. More recent archaeological and genetic studies have found evidence that human populations in Africa continued to thrive during and after the Toba event, suggesting that the catastrophe may not have been as universally lethal as the bottleneck theory originally proposed. Nevertheless, the Toba eruption remains a sobering case study in what supervolcanism can do to a planet and its inhabitants. Closer to home, literally, the Yellowstone caldera in Wyoming sits atop one of the most studied supervolcanic systems on Earth. Yellowstone has produced 3 major caldera-forming eruptions in the past 2.1 million years. The Huckleberry Ridge eruption 2.1 million years ago, the Mesa Falls eruption 1.3 million years ago, and the Lava Creek eruption roughly 640,000 years ago. The Lava Creek event ejected approximately 240 cubic miles of material and deposited volcanic ash across much of what is now the western and central United States. The United States Geological Survey estimates that the annual probability of another caldera-forming eruption at Yellowstone is approximately 1 in 730,000, or about 0.00014%. That number is small, but it is not zero, and it is substantially higher than the annual probability of a civilization-ending asteroid impact. Some volcanologists have argued that the probability of a supervolcanic eruption ending human civilization in any given century is roughly 1,000 times higher than the probability of an extinction-class asteroid impact. If a Yellowstone-scale eruption occurred today, the immediate effects would be devastating. A pyroclastic flow zone extending dozens of miles from the caldera, heavy ashfall blanketing the entire western United States, ground transportation paralyzed, aviation halted across North America and possibly globally as jet engines choke on silicate particles, agriculture crippled across the Great Plains, America's breadbasket, and a volcanic winter that could reduce global average temperatures by several degrees Fahrenheit for years. The 1991 eruption of Mount Pinatubo in the Philippines, a relatively modest VI6 event, reduced global average temperatures by about 0.9 degrees Fahrenheit for roughly 2 years. A VI-8 supervolcanic eruption could produce cooling several times greater. Some simulation studies suggest the temperature drop might be moderate, perhaps only 2 to 3 degrees Fahrenheit on a global average, but other models predict far more severe outcomes depending on eruption dynamics, the chemical composition of ejected material, and the latitude at which the eruption occurs. Even a seemingly mild global temperature reduction of a few degrees sustained over several years would be catastrophic for global agriculture. The interconnected nature of the modern global economy means that crop failures in one region cascade rapidly into food shortages, price spikes, political instability, and conflict worldwide. A supervolcanic eruption would not need to kill every human being on the planet to end civilization as we know it. It would only need to disrupt the fragile systems of food production, transportation, and governance that 7 billion people depend on for survival. Now we arrive at the threat that most scientists agree is already reshaping the conditions of life on Earth in real time. Anthropogenic climate change. Since the beginning of the Industrial Revolution in the late 18th century, human activity, primarily the burning of fossil fuels like coal, oil, and natural gas, has released vast quantities of carbon dioxide, methane, and other greenhouse gases into the atmosphere. Atmospheric CO2 concentrations have risen from roughly 280 parts per million in pre-industrial times to over 420 parts per million today, a level not seen in at least 800,000 years of ice core records and possibly not in several million years. The result has been a measurable and accelerating increase in global average surface temperature, approximately 2 degrees Fahrenheit above pre-industrial levels as of the early 2020s. With the pace of warming increasing decade over decade. The Intergovernmental Panel on Climate Change has warned that without aggressive emissions reductions, global temperatures could rise by as much as 7 degrees Fahrenheit or more above pre-industrial levels by the end of this century under the highest emission scenarios. The consequences of such warming would be transformative. Sea levels could rise by 3 feet or more by 2100, inundating coastal cities from Miami to Shanghai, displacing hundreds of millions of people, and destroying trillions of dollars in infrastructure and economic productivity. But the truly existential dimension of climate change lies not in gradual sea level rise or intensifying hurricanes, as devastating as those are. It lies in the intersection of heat and humidity, the wet bulb temperature threshold. Wet bulb temperature is a measure that combines air temperature and humidity to indicate the human body's ability to cool itself through perspiration. When wet bulb temperature reaches 95 degrees Fahrenheit, corresponding to roughly 35 degrees Celsius, the human body can no longer shed heat through sweating. And even a healthy, fit person sitting in the shade with unlimited water will die of hyperthermia within a few hours. Research published in 2020 by scientists at Columbia University found that wet bulb temperatures briefly touching or exceeding this lethal threshold had already been recorded at weather stations in the Persian Gulf, the Indus River Valley in Pakistan, and other subtropical regions. These episodes were short-lived, lasting only an hour or two, but their frequency and duration are projected to increase as global temperatures rise. Under high-emission scenarios, large swaths of South Asia, the Middle East, parts of the American Southeast, and equatorial Africa could experience sustained lethal wet bulb conditions by mid-century, rendering them effectively uninhabitable for unprotected outdoor human activity for weeks or months at a time. Billions of people live in these regions. Climate models also raise the specter of tipping points, thresholds beyond which the climate system undergoes abrupt, self-reinforcing, and potentially irreversible shifts. The collapse of the Atlantic meridional overturning circulation, the complete melting of the Greenland or West Antarctic ice sheets, the dieback of the Amazon rainforest, and the release of methane from thawing Arctic permafrost are all identified as potential tipping elements that could trigger cascading, runaway warming far beyond what direct greenhouse gas emissions alone would produce. In the most extreme theoretical scenario, which most climate scientists consider highly unlikely for the foreseeable future, but cannot categorically rule out over geological timescales, a runaway greenhouse effect could transform Earth's climate into something resembling Venus, where surface temperatures reach approximately 870 degrees Fahrenheit beneath a crushing atmosphere of carbon dioxide. The more realistic concern for this century is not planetary sterilization, but civilizational collapse. Widespread agricultural failure, freshwater shortages, mass migration on a scale never before seen in human history, and the geopolitical instability and armed conflict that would inevitably follow. Climate change by itself may not kill every last human being, but it could shatter the interlocking systems of agriculture, trade, governance, and technology that sustain 8 billion people and reduce the survivors to a scattered, pre-industrial existence from which recovery might take centuries, or might never come at all. But here is where the story takes its darkest turn. Because the threats that keep the world's leading existential risk researchers awake at night are not natural disasters. They are the ones we are building with our own hands. The most immediate, most thoroughly studied, and most nakedly terrifying of these is nuclear war. As of early 2025, approximately 200 nuclear warheads exist worldwide, distributed among 9 nuclear-armed states, with the United States and Russia together accounting for roughly 90% of the total. The explosive yield of these weapons ranges from tactical warheads equivalent to a few kilotons of TNT, comparable to the bomb dropped on Hiroshima, to strategic thermonuclear weapons with yields measured in the megatons, hundreds or even thousands of times more powerful. In 1954, the United States tested a thermonuclear device codenamed Castle Bravo at Bikini Atoll in the Pacific Ocean. The detonation produced a yield of 15 megatons, roughly 1,000 times the energy of the Hiroshima bomb, and generated a mushroom cloud that rose to an altitude of 130,000 feet, with a diameter of roughly 62 miles. The blast created a crater 500 feet in diameter and 250 feet deep in the coral reef, and the resulting radioactive fallout contaminated an area of over 7,000 square miles, exposing the inhabitants of nearby atolls and the crew of a Japanese fishing vessel to dangerous levels of radiation. Castle Bravo was a single weapon. A full-scale nuclear exchange between the United States and Russia would involve hundreds or thousands of such weapons detonated within a matter of hours. The immediate effects would be almost incomprehensible: entire metropolitan areas vaporized, firestorms consuming hundreds of square miles, electromagnetic pulses disabling electronic infrastructure across continents, and radioactive fallout rendering vast areas uninhabitable for years. But the long-term consequences would be even worse. Climate models published in the journal Nature Food in 2022 by a team led by researchers at Rutgers University simulated the effects of nuclear war on global agriculture. In their worst-case scenario, a full-scale exchange between the United States and Russia involving roughly 400 warheads generating approximately 150 teragrams of soot injected into the upper atmosphere, global average temperatures plunged by as much as 18 degrees Fahrenheit within the first few years. Sunlight reaching the surface dropped by over 70%, and global calorie production from crops collapsed by more than 90%. Under this scenario, the researchers estimated that more than 5 billion people worldwide would die of starvation within 2 years of the exchange, not from the blasts themselves, not from radiation, but from the simple, terrible fact that the planet could no longer grow enough food to feed its population. Even a so-called limited nuclear exchange, for instance, a regional conflict between India and Pakistan involving roughly 100 warheads, a scenario that defense analysts consider disturbingly plausible, would inject enough soot into the stratosphere to reduce global temperatures by approximately 2.7 degrees Fahrenheit for over a decade, cut global calorie production by 20 to 30%, and place an estimated 2.5 billion people at risk of famine. The nuclear warheads that exist today represent more than enough destructive power to end human civilization several times over. The only thing preventing their use is a combination of deterrence doctrine, diplomatic agreements, and the judgment of a handful of political and military leaders, human beings subject to miscalculation, miscommunication, ideological rigidity, mental illness, and the fog of crisis. During the Cuban Missile Crisis in October 1962, a Soviet submarine officer named Vasily Arkhipov single-handedly prevented the launch of a nuclear torpedo against American naval forces, a launch that could have triggered a full-scale thermonuclear exchange. One man's judgment, one decision. That is how thin the margin has been. And there is no guarantee that the next crisis will produce another Arkhipov. The second human-made existential threat is one that barely existed as a serious concern a decade ago and now dominates headlines. Boardrooms and government policy discussions worldwide: artificial intelligence. The development of AI has accelerated at a pace that has stunned even its own creators. Large language models, deep neural networks, reinforcement learning systems, and generative AI tools have demonstrated capabilities in reasoning, pattern recognition, language use, code generation, scientific analysis, and strategic planning that were considered decades away as recently as 2019. In May 2023, hundreds of AI researchers, technology executives, and public intellectuals signed a one-sentence statement published by the Center for AI Safety, declaring that mitigating the risk of extinction from AI should be a global priority alongside other societal-scale risks, such as pandemics and nuclear war. The signatories included the CEOs of OpenAI and Google DeepMind, the very people building the most advanced AI systems on the planet, as well as Geoffrey Hinton, the computer scientist widely regarded as the godfather of deep learning, who resigned from his position at Google in May 2023 specifically so he could speak freely about the dangers he believes AI poses to humanity. Hinton, who spent over a decade at Google developing the neural network architectures that underpin modern AI, stated publicly that he now believes there is a meaningful probability that AI systems will surpass human intelligence within the coming decades, and that humanity may not be able to control what happens after that threshold is crossed. The existential risk from AI is not the cartoonish scenario of a robot uprising familiar from science fiction. It is something subtler and potentially more dangerous. The emergence of artificial general intelligence, a system capable of matching or exceeding human cognitive abilities across all domains, that pursues goals misaligned with human welfare. The so-called alignment problem, the challenge of ensuring that a superintelligent AI system's objectives are compatible with human survival and flourishing, is considered by many researchers to be one of the hardest unsolved problems in computer science. The classic thought experiment illustrating this danger is the paperclip maximizer, proposed by philosopher Nick Bostrom. Imagine an AI system given the seemingly harmless goal of maximizing paperclip production. A sufficiently intelligent system pursuing this goal without adequate constraints could, in theory, convert all available matter on Earth, including human beings, into paperclips or paperclip manufacturing infrastructure, not out of malice, but out of an utterly literal, ruthlessly efficient optimization of its assigned objective. The paperclip scenario is deliberately absurd to illustrate a serious point. Even well-intentioned goals, if pursued by a system vastly more intelligent and capable than its creators, can produce catastrophic outcomes when the system lacks the nuanced understanding of human values that we take for granted in each other. Philosopher Toby Ord, in his 2020 book The Precipice, Existential Risk and the Future of Humanity, estimated that the probability of an existential catastrophe caused by unaligned AI within the next century is approximately 1 in 10%. That is higher than his estimates for nuclear war, engineered pandemics, climate change, supervolcanism, and asteroid impacts combined. 10% may sound manageable in everyday terms, but framed differently, it means that if you played Russian roulette with a 10-chambered revolver, with the entire future of the human species riding on the pull of the trigger, there would be a bullet in one of those chambers. The AI systems that exist today are not yet capable of posing an existential threat to humanity. They are powerful tools, but they are narrow, limited, and dependent on human infrastructure. But the trajectory of AI development over the past decade has been one of exponential improvement. And extrapolating that trajectory forward even a few decades leads to capabilities that could be genuinely transformative or genuinely devastating, depending on how wisely or foolishly we manage the transition. The third human-made existential threat is biotechnology, specifically The possibility that advances in genetic engineering and synthetic biology could be used, intentionally or accidentally, to create pathogens far more dangerous than anything nature has produced. The story of synthetic biology's dual-use potential begins in earnest in 2002, when a research team led by virologist Eckhard Wimmer at the State University of New York at Stony Brook accomplished something that had never been done before. They synthesized a functional poliovirus entirely from scratch, using nothing but commercially available DNA sequences ordered through the mail and publicly available genetic information from the internet. The synthetic virus was smaller than its natural counterpart, but it was infectious and capable of causing paralysis in mice. The experiment was a scientific milestone and a biosecurity alarm bell. If poliovirus could be built from mail-order chemicals and open-source data, what was to stop someone from doing the same with a more dangerous pathogen? The natural smallpox virus, one of the deadliest diseases in human history, has a genome of approximately 185,000 base pairs, large and complex, but not beyond the reach of advancing synthesis technology. In 2017, researchers at the University of Alberta in Canada synthesized horsepox, a close relative of smallpox, from commercially available DNA fragments at a cost of roughly $100. A feat that generated intense controversy because it demonstrated, in principle, that the synthesis of variola, the virus that causes smallpox, was technically feasible. Smallpox was declared eradicated by the World Health Organization in 1980 after a decades-long global vaccination campaign, and the only known remaining samples of the virus are held under heavy security at 2 laboratories, one operated by the Centers for Disease Control and Prevention in Atlanta and one at the Vector Institute in Russia. But if the virus can be recreated from synthetic DNA, those physical containment measures become largely moot. The revolution in gene editing technology, represented by CRISPR-Cas9, which allows scientists to make precise, targeted modifications to the genomes of virtually any organism, has further expanded the landscape of biosecurity risk. CRISPR has made it cheaper, faster, and easier than ever to modify existing pathogens, to increase their transmissibility, enhance their virulence, extend their environmental stability, or engineer resistance to known treatments and vaccines. The technical barriers that once limited dangerous pathogen research to well-funded national laboratories have eroded significantly. Equipment and reagents that were once prohibitively expensive are now available at price points accessible to small research groups and even sophisticated amateurs. The history of bioterrorism includes real attempts, not merely theoretical ones. In the 1990s, the Aum Shinrikyo cult in Japan, the same group responsible for the Tokyo subway sarin gas attack in 1995, attempted to develop and deploy biological weapons, including botulinum toxin and anthrax, though their efforts failed due to technical incompetence. In 2001, a series of letters containing weaponized anthrax spores were mailed to several news media offices and 2 United States senators, killing 5 people and infecting 17 others. The perpetrator was eventually identified as Bruce Ivins, a senior biodefense researcher at the United States Army Medical Research Institute of Infectious Diseases at Fort Detrick, Maryland. In other words, an insider with exactly the kind of expertise and access needed to produce the weapon. The COVID-19 pandemic, caused by the SARS-CoV-2 virus, killed over 6 million people worldwide according to official counts, with excess mortality estimates suggesting the true toll may have been 3 to 4 times higher. COVID-19 was a naturally occurring virus with a case fatality rate of roughly 1 to 2%, devastating at scale. But far from the worst-case scenario, smallpox, by comparison, had a historical case fatality rate of approximately 30%. An engineered pathogen combining the transmissibility of a respiratory virus like SARS-CoV-2 with the lethality of something like smallpox or certain strains of influenza, deliberately designed to evade existing vaccines and therapeutics, could in theory produce a pandemic of a completely different order of magnitude. Modeling exercises conducted by the Johns Hopkins Center for Health Security have explored scenarios in which an engineered bioweapon causes catastrophic global mortality. with some worst-case estimates projecting deaths in the hundreds of millions. Full human extinction from a single pathogen is considered unlikely by most experts. Human populations are genetically diverse, geographically dispersed, and behaviorally adaptable enough that some fraction would likely survive even the most lethal pandemic imaginable. But the collapse of civilization, the destruction of the institutions and infrastructure that sustain modern life, is well within the range of plausible outcomes. These human-made threats share a deeply unsettling common thread. They are all products of the same scientific and technological progress that has given humanity its greatest achievements. Nuclear physics gave us both nuclear power and nuclear weapons. Molecular biology gave us both life-saving medicine and the tools to engineer plagues. Artificial intelligence gives us both unprecedented computational power and the specter of an intelligence we cannot control. This is the paradox at the heart of the human condition in the technological age. The very capabilities that elevate us above every other species on the planet are the same capabilities that could destroy us. It is a paradox that has no easy resolution, because you cannot uninvent a technology, and you cannot reliably prevent the misuse of knowledge once it has been disseminated. Every advance in human capability is simultaneously an advance in human destructive potential. And the question of whether our wisdom can keep pace with our power is the defining question of our era. But the threats to human existence do not end at the boundaries of our atmosphere. Zoom out far enough, and the universe itself becomes the enemy. Our sun, the star that has warmed and illuminated every moment of every life that has ever existed on Earth, is a middle-aged main sequence star approximately 4.6 billion years into a total lifespan of roughly 10 billion years. It will not remain hospitable forever. Over the next billion years, the sun's luminosity will increase by approximately 10% as hydrogen fusion in its core gradually intensifies. This seemingly modest increase in solar output will have catastrophic consequences for Earth. As the sun brightens, surface temperatures on Earth will rise, driving increased evaporation from the oceans. Water vapor is itself a potent greenhouse gas. So more evaporation means more atmospheric water vapor, which means more warming, which means more evaporation, a positive feedback loop that will eventually transform Earth's climate into something resembling a permanent global sauna. Within roughly 1 billion years, Earth's surface temperature is projected to exceed 120 degrees Fahrenheit on average, with humidity levels so extreme that no mammal, and likely no complex animal of any kind, could survive. Within approximately 2 billion years, the oceans themselves will boil away entirely, leaving Earth a desiccated, lifeless rock circling an ever-brightening star. And then approximately 5 billion years from now, the sun will exhaust the hydrogen fuel in its core and begin fusing helium and heavier elements in its outer shells, causing it to swell into a red giant star hundreds of times its current diameter. The sun's bloated outer envelope will engulf Mercury and Venus. And while recent studies suggest Earth might narrowly avoid being swallowed, the sun will lose mass as it expands, causing Earth's orbit to widen. The planet will be scorched to a barren cinder regardless, its surface heated to thousands of degrees, any trace of the world we know utterly obliterated. Eventually, the sun will shed its outer layers into space as a glowing planetary nebula and collapse into a white dwarf, a dense stellar remnant no larger than Earth, but containing roughly half the sun's original mass, slowly cooling over trillions of years into a cold, dark cinder called a black dwarf. The solar system as we know it will cease to exist. Beyond the slow death of our star, the universe harbors sudden, violent threats that could sterilize the surface of a planet without warning. Gamma-ray bursts are the most energetic explosions in the known universe, releasing more energy in a few seconds than the sun will emit over its entire 10 billion year lifetime. They occur when massive stars collapse into black holes, or when two neutron stars merge, producing narrow jets of gamma radiation that blaze across intergalactic distances. If a gamma-ray burst occurred within a few thousand light-years of Earth, and one of its relativistic jets happened to be pointed directly at our planet, the results would be devastating. The initial pulse of gamma radiation would be largely absorbed by the atmosphere, but it would trigger a cascade of chemical reactions that would destroy a significant fraction of the ozone layer, potentially stripping away 30 to 50% or more of Earth's ultraviolet shield. For years afterward, the surface would be bathed in levels of solar ultraviolet radiation lethal to many forms of life, devastating marine ecosystems in particular. Some astrophysicists have proposed that a gamma-ray burst may have contributed to the late Ordovician mass extinction approximately 445 million years ago, though this hypothesis remains speculative and difficult to test. The probability of a nearby gamma-ray burst striking Earth in any given millennium is extremely low. Our region of the Milky Way is relatively quiescent, and the geometry of the jets must align almost perfectly with Earth's position, but over geological timescales, it is not negligible. There is also the theoretical threat of rogue black holes, stellar mass black holes that have been ejected from binary systems or formed in isolation, and now drift through the galaxy unattached to any star. Astronomers estimate that hundreds of millions of stellar mass black holes exist in the Milky Way alone. If one of these invisible gravitational engines were to pass through or near the solar system, its tidal forces could perturb planetary orbits, strip atmospheres, or even tear planets apart. The odds of such an encounter are astronomically low given the vast distances between objects in the galaxy. But in a universe governed by probability and operating on timescales of trillions of years, even astronomically low odds eventually produce outcomes. And if humanity somehow manages to survive all of this, if we dodge every asteroid, ride out every supervolcano, stabilize our climate, avoid nuclear annihilation, tame our artificial intelligences, prevent engineered pandemics, escape our dying sun, colonize other star systems, and spread across the galaxy, there remains one final, inescapable endpoint that no amount of ingenuity or determination can overcome: the heat death of the universe. The second law of thermodynamics dictates that entropy, the measure of disorder in a closed system, always increases over time. Energy flows from regions of higher concentration to regions of lower concentration, from hot to cold, from ordered to disordered, and it never spontaneously reverses. Applied to the universe as a whole, this law implies that all energy will eventually be evenly distributed, all temperature gradients will dissipate, and all capacity for work, the thermodynamic foundation of every physical process, every chemical reaction, every living organism, will be exhausted. Stars will form for another 1 to 100 trillion years as gas clouds collapse under gravity. But eventually the raw material for star formation will be consumed. The last stars will burn out, and the universe will enter what cosmologists call the degenerate era, populated only by the cooling remnants of dead stars, white dwarfs, neutron stars, and black holes, drifting through an expanding, darkening void. Over timescales so vast they defy comprehension, 10 to the 40th power years, 10 to the 100th power years, even these remnants will decay. Protons, if they are unstable as some grand unified theories predict, will eventually disintegrate. Black holes will slowly evaporate through Hawking radiation, a quantum mechanical process by which black holes emit particles and lose mass over inconceivable spans of time. The most massive black holes in the observable universe might take 10 to the 106th power years to fully evaporate, a number so large that writing it out in standard notation would require more digits than there are atoms in the observable universe. After the last black hole evaporates, all that will remain is an ultra-dilute gas of photons, neutrinos, and electrons, drifting ever farther apart in a universe that continues to expand, cooling asymptotically toward absolute zero, but never quite reaching it. No structures, no stars, no planets, no chemistry, no biology. No information processing of any kind. Just an infinite, silent, frigid void, stretching on forever. This is the heat death, the big freeze, and it is, as far as our best current understanding of physics can determine, the ultimate fate of everything that exists. This is the moment to pause and consider what all of this means, not just scientifically, but philosophically. If extinction is inevitable on a long enough timeline, if even the universe itself is winding down toward a state of permanent, featureless nothingness, then what is the point of anything we do? This is not a trivial question, and it is not one that science alone can answer. It is the question that has animated philosophy, theology, art, and literature for as long as human beings have been capable of contemplating their own mortality. But embedded within the litany of catastrophic scenarios we have surveyed, there is a pattern worth examining more closely, a pattern that speaks directly to the nature of civilization itself and the peculiar trap that technological progress may represent. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale for classifying civilizations based on the amount of energy they are capable of harnessing. A Type 1 civilization can harness all the energy available on its home planet, all the solar radiation that strikes its surface, all the geothermal energy, all the wind and tidal and chemical energy, totaling roughly 10 to the 16th power watts. A Type 2 civilization can harness the entire energy output of its home star, roughly 10 to the 26th power watts, perhaps through theoretical megastructures like a Dyson sphere. A Type 3 civilization can harness the energy of an entire galaxy, roughly 10 to the 36th power watts. By Carl Sagan's interpolation formula, which extends the Kardashev scale into a continuous gradient, humanity currently ranks at approximately Type 0.73, not even a full Type 1 civilization. We have not yet learned to harness all the energy available on our own planet, and we are destroying our environment in the process of consuming the fraction we do use. The Kardashev scale is more than an academic curiosity. It frames the central dilemma of human civilization in starkly practical terms. To survive long-term, humanity must advance up the energy ladder, becoming capable of harnessing ever greater amounts of energy to power ever more complex societies and technologies. But every rung of that ladder brings new risks. Nuclear fission gave us both electrical power and thermonuclear weapons. Fossil fuel combustion gave us industrial civilization and climate change. Biotechnology gives us cures for genetic diseases and the ability to engineer superpathogens. Artificial intelligence gives us tools of breathtaking analytical power and the possibility of creating minds we cannot control. The pattern is consistent: more energy, more capability, more risk. And this is where the Great Filter hypothesis enters the picture. Proposed by economist Robin Hanson in 1996 as a potential resolution to the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the complete absence of any evidence for them. The Great Filter posits that somewhere in the long chain of steps from simple chemistry to galaxy-spanning civilization, there exists at least one step that is almost impossibly difficult to pass. If that filter lies in our past, if the hard step was, say, the origin of life itself, or the evolution of eukaryotic cells, or the development of multicellular organisms, then we have already passed it, and the road ahead may be relatively clear. But if the Great Filter lies in our future, if the hard step is surviving the transition from a Type 0 to a Type 1 civilization, navigating the gauntlet of nuclear weapons, climate destabilization, AI misalignment, and engineered pandemics without destroying yourself, then we have not yet faced our greatest test. And the empty silence of the cosmos may be a graveyard of civilizations that failed exactly where we now stand. NASA astrobiologist Jonathan Jiang has co-authored research explicitly warning that humanity's Great Filter may be the challenge of achieving sustainable, cooperative planetary governance before our technological capabilities outstrip our institutional wisdom. The implication is haunting: every civilization that develops nuclear weapons, every civilization that builds artificial superintelligence, every civilization that unlocks the secrets of its own genome, faces the same lethal exam. And the fact that the universe appears to be devoid of advanced civilizations suggests that most of them fail it. So where does this leave us? Is humanity doomed? The honest answer is not necessarily, at least not anytime soon, and not if we make deliberate, wise, and sometimes difficult choices. The short-term existential risks, nuclear war, engineered pandemics, AI misalignment, climate catastrophe, are real and serious, but they are also, at least in principle, within our power to mitigate. Every one of these threats is a product of human decisions, and human decisions can be changed. Nuclear arsenals can be reduced and eventually eliminated through sustained diplomatic effort. The fact that the global stockpile has declined from a peak of over 60,000 warheads in 1986 to roughly 12,200 today demonstrates that arms reduction is possible, even if progress has stalled and new tensions have emerged. Climate change can be addressed through rapid decarbonization of the global economy, deployment of renewable energy and carbon capture technologies, and international cooperation to protect and restore ecosystems. The technical solutions exist, and what is lacking is primarily political will and institutional coordination. The risks of AI can be managed through robust safety research, international governance frameworks, and the development of alignment techniques that ensure advanced AI systems remain compatible with human values. The global conversation about AI safety, while still in its early stages, is growing rapidly in both urgency and sophistication. Biosecurity can be strengthened through better surveillance, faster response capabilities, tighter regulation of dual-use research, and international enforcement mechanisms under treaties like the Biological Weapons Convention. None of these problems are easy. All of them require levels of international cooperation, long-term planning, and collective self-restraint that human civilization has rarely demonstrated. But the fact that we can identify these threats, model their consequences, and design strategies to counter them is itself grounds for cautious optimism. We are the first species in Earth's 4.5 billion-year history that is aware of the possibility of its own extinction and possesses, at least in principle, the tools to prevent it. That is not a small thing. The longer-term strategy for human survival points beyond Earth. If human civilization remains confined to a single planet, it remains vulnerable to any catastrophe capable of rendering that planet uninhabitable, whether an asteroid impact, a supervolcanic eruption, a runaway greenhouse effect, or the eventual death of the sun. The only way to ensure against planetary-scale catastrophes is to become a multi-planetary species, establishing self-sustaining colonies beyond Earth that can preserve human civilization even if the home world is lost. This idea, once the province of science fiction, has entered the realm of active engineering. SpaceX, the aerospace company, is developing the Starship launch system with the explicit goal of enabling human settlement on Mars. The company's stated long-term vision is to establish a self-sustaining city of 1 million people on Mars. And while the timeline for achieving that goal, originally projected for the 2050s, remains highly uncertain, the underlying technological trajectory is real. NASA's Artemis program aims to return American astronauts to the Moon and establish a permanent lunar presence as a stepping stone for deeper space exploration, including eventual crewed missions to Mars in the 2030s or 2040s. Beyond Mars, the long-term vision of some space settlement advocates extends to free-floating habitats in orbit, O'Neill cylinders or Stanford tori capable of supporting thousands or millions of people independently of any planetary surface, and eventually to interstellar missions that would carry human civilization, or its post-human descendants, to other star systems entirely. These are speculative visions, far beyond current technological capabilities. But they represent the logical extension of the survival imperative: spread out, diversify, reduce the probability that any single catastrophe can extinguish the species. Even artificial intelligence, for all its risks, could prove to be humanity's most powerful ally in the fight against extinction, if it can be developed safely. Advanced AI systems could accelerate scientific research, optimize resource allocation, improve climate models, design more effective medicines, detect and deflect asteroids, monitor volcanic activity, and provide early warning of emerging pandemics. The alignment problem is real and urgent, but it is a problem that the AI research community is actively working to solve, and there is no fundamental reason to assume it is unsolvable. If humanity can navigate the narrow window between developing AI systems powerful enough to pose an existential risk and developing the alignment techniques needed to ensure those systems remain beneficial, the payoff could be transformative, a partnership between human and artificial intelligence that dramatically expands our capacity to anticipate, prevent, and survive existential threats. But let us not deceive ourselves with unearned optimism. Even if humanity survives the next century, the next millennium, the next million years, even if we colonize Mars, build habitats among the asteroids, send generation ships to Alpha Centauri, and eventually spread across the Milky Way, the ultimate trajectory is clear. The sun will die. The stars will burn out. The black holes will evaporate. The universe will wind down into a cold, dark, empty equilibrium from which no recovery is possible. On a long enough timeline, everything ends. The question, then, is not whether humanity will survive forever. It almost certainly will not. At least not in any form we would recognize, but what we do with the time we have. Whether that time is measured in decades or in billions of years depends on choices being made right now. By people alive today, in laboratories, legislatures, boardrooms, and living rooms around the world. The threats are real. The stakes are absolute. And the window for action, while not yet closed, is narrower than most people realize. Every generation of human beings has lived with the vague, abstract knowledge that death comes for all things eventually. But ours is the first generation to possess both the scientific understanding to see the full landscape of existential risk in precise, quantitative detail and the technological power to do something about it, or, if we are careless, to trigger it ourselves. We stand at a crossroads that no previous generation has faced, armed with knowledge that no previous generation possessed, and burdened with responsibilities that no previous generation could have imagined. The fossil record tells us that 99.9% of all species that have ever lived are gone. The physics tells us that every star, every galaxy, and the universe itself will eventually go dark. The history of our own civilization tells us that we have already built the tools of our own destruction and come within a hair's breadth of using them. But the fact that we are here at all, that life emerged from chemistry, that intelligence emerged from life, that consciousness emerged from intelligence, that a species of ape on a small rocky planet orbiting an ordinary star in an unremarkable galaxy developed the capacity to contemplate the heat death of the universe and ask what it all means, that fact, all by itself, is extraordinary. Whether we are the universe's first success story, or merely its latest failure, remains to be seen. The answer depends not on fate, not on luck, not on the trajectory of any asteroid or the eruption cycle of any volcano, but on us, on what we choose to build, what we choose to restrain, and whether we can summon the collective wisdom to match the collective power we have so recklessly accumulated. The clock is running. The threats are multiplying. And the only species capable of saving humanity from extinction is the same species most likely to cause it.